Hello, science family. We are going to talk about intermolecular forces today. And the idea behind this isn't the bonds that create compounds, but the actual forces that hold molecules near each other together. So for example, like water. Why, when there's a little tiny molecule of water, will another tiny molecule of water hang out around it? We're going to get into that with 3 different types of forces today that make a difference in the end. So let's go. All right, to talk about these intermolecular forces, these are really these tiny little forces between covalent molecules, all right? For short today, we're going to call them IMF, for intermolecular forces. But the reason we would even care about them is because if intermolecular forces didn't exist, then you would never have any compounds exist as a solid or a liquid. These things would just be flying around all over the place, and they would never interact between each other, keeping them close together and allowing them to become liquids or solids. So really, these intermolecular forces almost allow these molecules to stick together. All right? So the 3 types we're going to talk about today are all going to help make liquids or solids so that things can stay near each other. All right? The first 2 we're going to talk about are actually the weakest type of forces. They're called London dispersion forces and dipole interactions. And for some reason, we put them together and call them overall van der Waals forces. But the important part is that I'm going to need you to know the difference between a London dispersion force and dipole interactions. And both of those, 2 of those, are going to be under what we call, again, the intermolecular forces. So let's jump into those and see what they are individually. Let's start with the weakest type of intermolecular force. We call them the London dispersion forces, okay? And how this works is simple. Think of something like iodine. Iodine naturally combines with itself to make this covalent compound, all right? So these molecules of iodine, because the way electrons naturally move around in a molecule, sometimes iodine molecule is going to have a positive and a negative end because the electrons aren't always perfectly spaced out. So that makes one side of the molecule slightly positive while the other side is slightly negative. Again, the reason for that is on the slightly negative side, maybe for a little split second, there's more electrons on that side than on the other side. And because of that, we get these slightly negative and slightly positive ends of the molecule. Now take a look. We know that positives and negatives attract. So between this negative side and this positive side of the iodine molecules, they actually attract each other a little bit. Again, this is extremely weak, but because of it, example like noble gases are going to hang out near each other because of these London dispersion forces. So even though gas particles, we know, go all over the place and bounce around, don't forget that these little London dispersion forces will casually have them attracted to each other so that they don't completely flow away from each other. So when gases kind of hang out around themselves, that's really because of something we call these London dispersion forces. And they have to do with the positive and negative ends of molecules being attracted to each other. By the way, we call that positive and negative end a dipole. So for example, in this molecule right here, the positive end and negative end of the iodine is called a dipole, just because it has a positive and negative end. So that's a vocab term that we'll get more used to, dipole. Again, if we could diagram that out, we know that inside of an atom, there's the nucleus, and then there are the electrons on the outside. Sometimes, though, the electrons don't perfectly scatter around, so maybe there's more electrons on this side of the nucleus. That makes it more negative on this side and more positive on this side. We call that positive and negative side a dipole. And the dipole just means 2 poles, or a positive and negative end. Now, if we have atoms that have a positive and negative end, these negative and positive ends between elements or molecules slightly attract each other. We call that the London dispersion force. All right, the second type of intermolecular force are called dipole interactions. And these are a little bit stronger than London dispersion forces. Sometimes molecules are called polar. Poles meaning positive and negative ends. So sometimes they have a positive and negative end, and because of that, they're actually going to attract to other molecules that have a stronger positive and negative end. Take, for example, this HCl, which is hydrochloric acid. Hydrogens tend to have more of a positive charge, and the chlorine tends to have more of a negative charge. The reason for that, chlorine is more electronegative, so it pulls on electrons more. If you take a look at this hydrogen, it's going to be more positive, and this chlorine is going to be more negative. Because of that, you are going to have that attraction between the polar molecules, that positive and negative end. So that's going to be called a dipole interaction. Again, it's even stronger than the London dispersion forces because overall hydrogen is always slightly more positive and chlorine slightly more negative. So these polar molecules always end up having the slight positive and slight negative end, and because of that they attract to each other. So dipole interactions is the next intermolecular force. By the way, the London dispersion force and the dipole interactions both fall under the category of van der Waals forces. Not super important for you to know, it's just more of a labeling thing, but London dispersion forces and dipole interactions are both two of the weaker intermolecular forces. Dipole interactions are a little bit stronger. If we take a look at this picture, I think it does a great job of showing you we have polar molecules here, a positive and negative end, a positive and negative end, and because of that positive and negative end, you see these interactions, they're attracted to each other, all right? This allows for molecules to stick around each other and instead of floating away from each other. And remember, because of that, it allows for the object, instead of floating away as a gas, all right, it is attracted to each other enough that maybe it stays as a liquid and stays as a puddle on the ground instead of just evaporating immediately and turning into a gas. So remember, London dispersion forces and dipole interactions allow molecules around each other to stay as a liquid or sometimes even a solid if it's strong enough and the interactions are strong enough. The other type of intermolecular force that we're going to learn about is called hydrogen bonding. And this is the strongest of the intermolecular forces that we're going to talk about today. Whenever hydrogen is next to and bonded to a fluorine, oxygen, or nitrogen, there is a very, very strong dipole, meaning that between like the oxygen and the hydrogen pulls way more on the electrons than hydrogen does, making it more negative and the hydrogen more positive. Because of these guys, because remember, fluorine, oxygen, and nitrogen are very tiny and therefore love to pull on electrons, they become more negative, creating this very polar molecule or creating this strong dipole of positive and negative, all right? So if hydrogen's with fluorine, oxygen, or nitrogen, you create these strong dipoles, which means that we have even stronger interaction between positive and negative. Here's a great example of hydrogen bonding between water molecules. The oxygens are more negative and the hydrogens are more positive. And because of that, they have these strong interactions between the positive hydrogens and negative oxygens. So this is an example of hydrogen bonding, an example of why water, when it spills on the ground, it stays as a puddle and water molecules are attracted to themselves. That strong hydrogen bonding makes that happen. Now, because of hydrogen bonding, we can get into something we call cohesion and adhesion. Because water molecules have such a dipole, a positive and a negative side, water molecules like to stick to itself, which we just showed in the last slide. We call that cohesion when water sticks to itself. But because water also has a strong dipole, positive and negative, it also creates what we call adhesion. Adhering to something means sticking to it. So water droplets like to stick to a lot of things besides itself. It sticks to blades of grass. It sticks to your arm and body when you take a shower. We call that adhesion, and it's all because of hydrogen bonding. Water being stuck to itself because of cohesion creates a phenomenon called surface tension. If you've ever tried to put a paper clip on top of the water, even though a paper clip is more dense than water, if you lay it just right, it will sit on top of there. It's almost like the top of water creates this skin or this barrier on top of the water. And it's because the water molecules bind together and attract to each other through hydrogen bonding, and it creates this little film on top that you can set things on. That's called surface tension, and it's because of hydrogen bonding, that third intermolecular force we talked about. Hydrogen bonding also gives molecules, the stronger the hydrogen bonding, the higher the boiling point, meaning that you need to create a higher temperature in order to create more energy in order to break apart those liquids and turn into a gas. So the higher the boiling point for a covalent compound, usually it's the ones that have hydrogen bonding involved. All right, so if you look at this chart, all right, something like water, because oxygen and hydrogen create such a strong hydrogen bond, because hydrogen's more positive and oxygen becomes more negative, it takes even more higher temperature and energy to actually boil it, because you have to break those hydrogen bonds. So the stronger the hydrogen bond, the higher the boiling point. Something crazy as well is that when water freezes, it actually gets bigger and expands when it turns to ice. That is very rare. Most things that freeze get closer together, but because of hydrogen bonding and the way that water lines up with itself, it actually makes it a little bit larger in volume. So strangely enough, water expands when it turns to ice and it becomes less dense because it spreads out more. That is all because of hydrogen bonding as well. The last thing that's important is that water is often called the universal solvent. And the reason it's called that is because so many ionic compounds that turn into electrolytes can break down in water. The reason for that, since water has those positive and negative ends to them, it likes to break down other things like ionic compounds that naturally have the positive and negative ends. So water likes to surround them with the opposite charge and pull them apart. So water as a solvent is very natural because it does such a good job of breaking down things that are ionic compounds. It also can dissolve molecules, but not as well as ionic compounds because, again, ionic compounds have those charges. All right, so today we talked about intermolecular forces, London dispersion forces, dipole interactions, and hydrogen bonding. And they all help us in understanding why some covalent compounds like to stick near each other and eventually form a solid or a liquid instead of all of them just escaping as a gas. Them sticking together creates their own properties. Thanks for listening, Science Fam, and hopefully this gave you a little better insight into some of the ways that water works. Have a great day.